All right, number 9. So all right, so the baseball player hits a pop fly. So the idea is to go straight up. And we're asked about 2 different things here. It asks, what is the maximum height of the ball? And what is the speed of the ball when it is 40 meters above the bat? Let's do the first question, which is, what is the maximum height of the ball? I'd start by saying that what kind of energy does the ball have when it leaves the bat? Kinetic. We were told it's moving at 35 meters per second. So kinetic energy seems like the right choice there. I'm going to go ahead and go out on a limb here and say you guys probably forget to do this all the time, but you shouldn't. I'm going to set that as my reference level. I'm going to say that's 0. That's where the starting point is. That way there's no gravitational potential energy there. All right? If it goes straight up, it's going to eventually stop. How much kinetic energy does it have when it's stopped? 0. Is it above the reference level, though? All right, so I'm thinking it now has all gravitational potential. Is it pushed up against any springs? No, so there's no elastic potential energy here. If nothing took the energy out of the system, then the kinetic energy we have here has to be equal to the potential energy we have here. So I'm going to go with mgh equals 1/2 mv squared. What's h? I don't know the answer. What is h? 61? Okay. 61 meters. Now, the reason I'm stopping and I want to make sure I know how high this is because of the next question. The next question, what is the speed of the ball when it is 40 meters above the bat? I needed to make sure that the ball actually makes it 40 meters above the bat. You understand, right? If it didn't have enough energy to make it there, when we did this problem, we wouldn't have gotten a 40. It would have been less than that. I'm throwing that out there because you guys tend to get really weird when answers seem odd. So if I'd asked, what is the speed of the ball 80 meters above the bat? You would have to say, the ball never gets 80 meters above the bat. And that's just as good a question as the one that's asked here. So knowing whether or not it actually makes it 40 meters above the bat probably is part of what you should be able to do. But let's just say, okay, let's say 40 meters is here. When it is 40 meters above the bat, it is below this. And the reason I'm saying that is because it's going to have gravitational potential energy there, but that's not going to be all of the energy. Where's the other energy? Kinetic. Yeah, there's no springs, so it still has some kinetic energy that has not yet been transformed into potential energy. This is still how much energy it has, so I'll say mg times 40 plus 1/2 mv squared has to equal 1/2 m times 35 squared. Is that good for you? And you can do the work, I don't have to finish it? Okay, excellent. I'll try and draw this, but there's a spring here. And all right, so something like this is the arrangement we have. They indicated that this is 4H and this is 3H. Do I just need to do D and E, or would you guys like me to do all of it? Do whatever you guys ask. Find an expression for the minimum speed of the cart in order to make it to the top of the first hill. All right, well, the minimum speed of the cart would assume that the cart, when it's down here at the bottom, has nothing but kinetic energy because it's at the lowest place in the cart's motion. But the minimum speed would be the speed necessary to get the cart up here to the top so that it has no velocity. It's just enough to get up there. That'd be the minimum speed necessary, so that all of this kinetic energy is down here at the bottom is going to equal the gravitational potential energy here. So I'll set these equal and get mg times 4h equals 1/2 mv squared. And this is the minimum speed to make it over the top of the hill. Cancel out the m's and multiply by 2 and take the square root. And I think I'm going to get the square root of 8gh. Any question about that? Go on to question B. The spring of spring constant K is located on a landing on the opposite side of the hill. What is the speed of the car just as it makes it to the spring, assuming it successfully just made it over the top of the hill? So I'm assuming that we have this amount of energy. All right? Everybody understand what I'm saying? That's how much energy we gave the car, just that minimum amount. And now the car is over here, about to hit the spring. Is the car above the baseline or above the reference level? So it has gravitational potential. Is the car moving? Yeah, because they're asking how fast it's going. I think that's reasonable. It's below the highest point too, so whatever it has less gravitational potential, that energy must be in the form of kinetic or elastic, and it has not pressed up against the spring yet, so there is no elastic. So I think the amount of energy we have here is going to be equal to the amount of energy we have here. So I'll say mg times 4h has to equal mg times 3h plus 1/2 mv squared. Going to subtract, yes.
I did it because it just as it makes it to the spring, so I thought that and then it was touching it, so it had to be elastic.
Well, even if it's just touching the spring, elastic potential energy is based on how much the spring has been compressed. If the spring hasn't been compressed any, then there's no energy in the spring. So if it's just touching the edge of the spring, no energy in the spring yet. You have to displace the spring for energy to be stored in the spring. And actually, the way I'm supposed to say it is, you have to displace the spring for energy to be stored in the spring cart system. I'm saying it like that because that's how it's going to be on your test. So when we talk about potential energy, we talk about it's a relationship between two or more things. So for elastic potential energy, it's going to be the relationship between the spring and the cart. Gravitational is the relationship between the earth and the cart. So that's the way they'll phrase it. So I'm just saying when I tend to use AP problems, or I try to make mine sound like AP problems, they're going to make that reference. Does that make sense? All right. So subtract the mg3h from both sides, and I'll get mgh equals 1/2 mv squared. And that just means v is the root of 2gh. Keep going. What is the maximum compression of the spring in terms of m, h, and k, and any fundamental constants? All right. That suggests that there is another future where the spring now has been compressed by the car. Maximum compression is going to occur when the car comes to rest against the spring. Right, if the car's not at rest, then it's either still compressing the spring or it's moving away from the spring. So maximum compression is going to be when the car stops. So there's no kinetic energy. There's still gravitational potential energy because we're still 3h above the reference level. But now we also have elastic potential energy. So our total amount of energy is still mg times 4h. But now I have mg times 3h plus 1/2 kx squared equals mg times 4h. I want to solve that for x. So I subtract the mg3h from both sides and get just mgh. Multiply both sides by 2 divide by K. And then take the square root of both sides. And there's a lot of algebra here. You guys would benefit a little bit by doing more of your algebra in smaller steps, just a little at a time. I've looked at your tests, and that would help you guys out a little bit. So, again, it's just a conservation of energy problem. We found the limiting factor, which was the velocity, and then used that for conservation of energy, setting the energy here equal to the energy here. And then substituting in the limiting factor for the velocity. Solid question. Now it says, is there more or less than the compression of the spring from part C? I think is what it really meant. It's going to be more, right? What was your answer for part C? So clearly it's bigger. And that should make sense. When we did the question C, there was no kinetic energy at the top. If we wanted to have some kinetic energy at the top, we will have to add more energy into the system. So, all right, so this is delta X, and it's either 5 or 12. Right? Then the box makes it to here. By the time it makes it here, the box has acquired some velocity, right? I just don't know how much. Now, there's an unbalanced force acting on the box until it makes it to the frictional section, right? When it makes it to the frictional section, there will also be an unbalanced force acting this way on the box. And that unbalanced force will be just friction. Correct? So, during the time that the box is being pulled on by the 150 Newton force, since the force is unbalanced, the work done is going to equal the change in kinetic energy. Right? When it reaches the section where there's friction, the work done by friction is also going to equal the change in kinetic energy. All good so far? All right. The work done by friction is going to be friction times some distance. I don't know how far the box will slide being brought to rest. Okay? Times the cosine of 180 degrees. But that's also going to have to equal the change in kinetic energy. Now, we don't know the size of the frictional force, and we don't know how far the box slides. But it didn't ask for either of those. It asked for the work done, right? So I can find the work done two different ways. I can find it by multiplying the force times the displacement times the angle. Or, if it's the net work being done by that force, I can just find the change in kinetic energy. In order to know that, I have to know what the kinetic energy is at the start of the frictional patch and how much kinetic energy it has at the point where it stopped. Well, I think I know part of that. I think when it stopped, it's going to be 0. So I'm looking for how much kinetic energy it has at the start of the patch. Everybody follow along with that argument so far? All right. It acquires that kinetic energy over here. Right? That's where it gets that kinetic energy because you pulled on the box with 150 Newton force. In fact, we know that part explicitly. It's 150 newtons times the displacement of either 5 or 10. We don't know that part. You're just going to pick 5 or 10. I'm sorry, 5 or 12. Times the cosine of 30 degrees. And that has to equal the final kinetic energy minus 0. Isn't this kinetic energy this kinetic energy? Or the amount of kinetic energy it acquires by being pulled on by that force is going to be the amount of kinetic energy it has when it hits the part with friction and slows to rest. So that's the answer. I know that confuses you, but look at what you have to do. This is the amount of kinetic energy it has. This is how much energy the box has when it reaches the point where it hits friction. How much work does friction have to do to stop that box? Well, minus whatever that is. That's how much work has to be done by friction to bring the box to rest. That's it. This is how much energy the box has. Work is energy. It's how you change something's energy. So when I did work on the box, I gave it that much energy. If you want a numerical answer, well, choose whether it went 5 meters or 12 meters and put a number in there. But that part's not the important part. The important part is that we gave the box this amount of energy, and friction is going to take that amount of energy away. Was there more? Oh, there was another question. If the box slides 20 meters coming to rest, what was the size of the frictional force? All right. Now we have to choose. Did you want this to be the 5-meter one or the 12-meter one? I'm not going to do both. So, I'm just going to turn around and tell you to tell me what does that equal then. I'm sorry, that was a whole lot of I can't hear what you said. 1,558.8. That's for 12. That's what she said for 12. Are we good for 12? Okay, so this is how much joules of energy the box has. So over here, come back to this. Friction has to bring the box to rest, knowing it started with 1,558.8 joules of energy. Well, it says it does so in 10 meters. That's it. Looks like the frictional force has to be 156 newtons. In fact, I think I could go one step further and ask you to find what the coefficient of friction is. Why not? We know the box is 30 kilograms. But I'm not going to go that far. This is enough work. The look on your face says that's enough. So that's enough. No, your face. You look scared. Yeah. You look a little nervous. All right. It's just physics problems. I'm sorry. The problem says 20 meters. Sorry. I put 10. I'm not even sure why I put 10. But the problem says 20. So 70 what? 76? 77? All right, 77 newtons. There. Let's probably read the problem first. What? You're going to ace it tomorrow? How many minutes do I have for the bell rings? Because I need to show you something. All right. I'm going to take this little discussion back over if you don't mind, okay? I'm bringing up a problem because one of the things that you guys are terrible about is remembering stuff we've already done. I drew it quick, but I have a little ball up there, and I want to know in which case would the ball travel the furthest away from the table. Are you hearing my question? Now, I would not jump to a conclusion here, especially since I'd probably ask for you to prove it. Because you can make all sorts of conjectures, right? Table 1, the ball will be going slower when it leaves the table. Would you agree? I think you should be able to make that kind of conjecture, because when the ball makes it to here, it changed height less than when this ball makes it to here, right? So this ball is probably going faster off the table than this ball is. But the ball that leaves table number 1 is in the air for a longer period of time. So although it's traveling slower, it gets to travel for a longer period of time before it reaches the ground. You understand why which table will launch the ball farther isn't necessarily a straightforward question. You could prove it. You could do the work. You could find Vx, and from there do a projectile problem and find out how long it takes for the thing to reach the ground. You should do this. And it's not very much to do. Pick one side. Because if you pick one side, you can always just change the subscripts from 1 to 2 to compare it to the other side, correct? So try it. Figure out how fast would this be going. And we don't have that much time because it's Thursday, right? So special schedule means I've got 5-6 minutes. But have you done this a few times already to know that, okay, I could set the top of the table as my reference level? And that would mean I have mgh1 worth of gravitational potential energy there. Do you see what I'm doing? If you do, great. If you don't, you're in trouble. Because over here I'm going to have 1/2 mvx squared. And we've done this many times, or you should have. So Vx equals the square root of 2gh1. You set them equal to each other and solve for the velocity. This has happened 3 times just today in the homework we've been doing. It's usually a square root of something times gh. The next part of the problem is a projectile problem. And here's why I'm bringing it up. You guys forget this stuff. Do you remember how to solve a projectile problem? Do you remember to set up a chart and have the vertical side and the horizontal side? Do me a favor. Take 2 minutes and tell me how long it takes to reach the ground. And if it takes you 2 minutes, you didn't memorize something I told you to memorize earlier in the year. All right, so that was situation 2, and we found the network by just doing the change in kinetic energy, but we went a long way around it to figure out the tension as well and calculated the 2 works, and it still comes out to be 12,000. So I think we're good so far. Keep going?
No, I think it's okay.
All right. Well, I think we did all of part B, right?
Mm-hmm. That's what I was saying. I answered the questions already.
Okay. I guess we did all of it. All right, fine. So there. Yay, fun times.
Thank you.
You're welcome. Now, we could have, if we had accepted this as the answer, we could have found the force a different way. And we could have done this one first and then just added the 12,000 to it to get this one and then use that to find this force. We could have worked this backwards if we wanted. I think it might be I'll be happy to go to 9 right after this. But since I'm still on this page, I've been a little surprised by it. So I'm going to take this as the moment that I wanted to work on something else, and then we'll go back to our regularly scheduled homework review. I'm trying to draw it like it looks there, but not great, but you guys get the gist. The point was that this height and this height were the same. Okay. And it asked a couple of pretty basic questions like, does either ball have more potential energy than the other? And that's a subjective question. So if you put the ball here, you put the ball here, would you say that ball A has more potential energy than ball B, that ball B has more potential energy than ball A, or are they the same? Now, I think you ask yourself, well, compared to what? And they tell you to compare it to point P, indicating that's the same height. So compared to rolling to this point, they would have the same potential energy, since that's where the ball ends up at the end of each ramp. However, which ball gets there soonest? B gets there soonest. And I don't think all of you would have said that. But ball B gets to go here, where it will clearly be traveling faster than ball A. Right? Now, it might come back up to that same height, but because it's traveling faster along this portion of the route, it might get to the end of the ramp sooner. Like, it's not unreasonable that it would, because it'll have a period of time where it's traveling faster. But yes, when they both get here, they have the same velocity when they make it to this point. We got it? These are the things to think about. Remember, energy doesn't tell us very much about time. You need to consider time portions of this elsewhere.
So does the change in direction that B has not make a difference?
What do you mean the change in direction?
It has the little thing, which.
At the very end, it comes back up and it slows down.
Yeah.
But it doesn't necessarily, it means it's still going to have the same velocity when it's here as this ball will have here.
Okay.
Because they both have the same change in height.
Okay.
Now, I'm going to add something to this, something that I am very sure you guys have not thought of. All right, you guys can kind of see I have two different tables. And please do not jump to an answer. Be thoughtful. In which of these two situations would the ball land further away from the table? Table 1 or table 2? I'd be careful about your argument here. In table 1, the ball will be traveling slower when it leaves the edge of the table, but we'll have more time in the air. Table 2, the ball will be traveling faster when it leaves, but we'll have less time in the air, which is why I don't think you should jump to a conclusion, right? You should be thoughtful about it. You can figure it out. You can run the numbers. You could consider how you would figure out where it lands. You should know things that would assist you. Like, I should be able to ask you to tell me, where does it land on the ground in terms of H1, H2, fundamental constants, stuff like that. And you should be able to do it. And I think you could do the energy portion of this, but I think you have forgotten how to do anything related to stuff that wasn't last week. So projectile motion might be difficult for you because you haven't thought about it in a while. Now, I'll help a little bit here, but you're going to have to do a little of this work. For example, I think we can say that there's gravitational potential energy and kinetic energy here, and think of the tabletop as the reference level. Any question about why I'm doing that? If you're paying close attention, you realize that by doing that, I can find out that mgh1 equals 1/2 mv squared. So V1 equals the root of 2gh1. You've done that energy problem a couple times already. I would hope that that one isn't too difficult to do. And you can do the same thing for the other side. The problem is that now that it's being launched at a horizontal velocity, you've got a projectile problem with vertical and horizontal. And if you guys are anything like first period, you're going to fail miserably here because you have forgotten to do something that I asked you to do. I want you to figure out how long it takes the marble to reach the ground. If it takes you more than 30 seconds, you didn't do something I asked you to do. Figure it out. Again, you should memorize how long it takes something to reach the ground. You should realize that, yes, there are questions related to energy here, but there's also good old-fashioned kinematics built into this. There's no way around those questions. Yeah, you can produce where it's going to strike the ground, but you need to remember all of this stuff. Remember, every test is cumulative. This is cumulative. And don't lose sight of this fact that they both started from the same height. Now, I'm not saying this is on your test, but I'm saying this is the kind of stuff you tend to do badly on because you get broadsided by it. But is there anything out of bounds here? You'll say, wow, that was a really hard test. I'm just trying to show, I can't show you every possible situation. You'll say there's too much homework to do. But this is what I'm thinking that little ramp problem that I gave you as situation 1 is hinting at. All right, well, that was fun for me. I'm doing number what? 9. All righty. Fun times. Fun times. All right, number 9. A baseball player hits a pop fly. Say that the baseball leaves the bat at 35 meters per second. Did you set the reference level to be the bat? Well, that's what I would probably do. I'd probably set this to be the reference level. And that way, when it leaves the bat, it doesn't have any gravitational potential energy because it's at the bat. It has all kinetic energy. Now, it asks what the maximum height is. Well, I would assume the maximum height will be the place in which there is no more kinetic energy, where all the energy is in the form of gravitational potential. Because if it had kinetic energy, that would mean it's either still going up or is already starting to come down. So when it has no kinetic energy, that's got to be the maximum height. You could also do this as a motion equation problem. There's no reason why you can't. Initial velocity 35, final velocity 0, find h, the acceleration is g. It's faster to use energy, but you don't have to use energy to answer these questions. But I'm going to go ahead and use energy because I've already got it written out. So m, g, h, and I'll put h max so I can tell the difference, is equal to 1/2 mv squared. The solution to this should tell me the maximum height. And based on last class period, I think this is like 61 meters. Would somebody agree with that? 62? Now, the next part of the question asks, how fast is it going when it's 40 meters in the air? I think it's important that you know how high it goes. I'm saying this because when it's 40 meters in the air, it's going to have gravitational potential energy. If it makes it this high, if you didn't know that it already went past this point, then you would probably get an answer that would be weird. Like, what if I asked you, how fast is it going when it's 80 meters above the ground? Well, it can't reach 80 meters above the ground. you'll probably get some kind of weird answer, probably some kind of negative in there that doesn't seem to be where it's supposed to be. And you'll have to take the square root of it. That's how you can tell that there's probably something wrong. Because I could just as easily ask you, how fast is it going at 80 meters? And if you didn't know that the maximum height was 62 and you just went right to that problem, you wouldn't know you're working wrong. So having you find the maximum height first helps you establish that, okay, it can be 40 meters above the ground. In fact, it will pass that point on the way up and on the way down. But that means it will, whatever energy is not gravitational potential is going to have to be kinetic. Well, that means mg times 40 plus 1/2 mv squared equals 1/2 m35 squared. I'm still using this as my original amount of kinetic energy. I'm just now figuring out my new velocity. Is that enough?
Yes.
Alrighty, awesome. All right, so we have figured out the minimum speed to get to the top, and then we figured out how fast it's going if it rolls from the top to where the spring is. What is the maximum compression of the spring in terms of mhk and any fundamental constants? Well, I think that brings up a different situation in which now the box has compressed the spring. So we're over there now. No kinetic energy. We want the maximum compression of the spring, so the cart can't be moving. Because if it were moving, then it would either still be compressing the spring or the spring would be relaxing and going the other direction. It does have gravitational potential because we're still above the reference level. And it has compressed the spring now, so we do have elastic potential. I'm still going to base this on the fact that our total amount of energy was mg4h because it made it from the top of the hill to here. So I'll have mg times 4h equals 1/2 kx max squared plus mg times 3h. And we're supposed to solve this for x. So subtract the 3h from both sides, and I'll get mg times h equals 1/2 kx max squared. And multiply by 2 and divide by k, and get that x max equals the square root of 2mgh over k. All good? All right, so it goes on. This time the car begins its run from the spring. The spring is pulled back far enough for the car to make it over the hill. The hill, however, is circular with the radius of curvature of h. What is the maximum speed the car can successfully make it over the hill and not lose contact with the ground? I like this question. I like it a lot. If I were you, I would probably recognize that the reason I like it is because it brings in other stuff. So I'm going to move this stuff out of the way because I don't need this anymore. This is all different. And let's can leave this here. That'll be all right. The first thing I want to impress upon you is that we have a condition that has to be met. For the car to be able to stay in contact with the ground and to make it over the top of a circular hill, then a condition has to be met. I'm saying this because there are clues here as to what you have to do. Circular hill, circular motion is probably what they're talking about, and they're talking about a threshold. This seems like the net force problems we've done with centripetal motion, the car going over the hill problem. And this is it. So I think there are two forces acting on the cart at the very top. There's going to be a normal force upwards and a gravitational force downwards. The clue that this is a circular motion problem is the fact that they talked about it being a circular hilltop. That's the clue. And the fact that there is a limited velocity. That's another clue that means you have to use this. This is a throwback, and some of the things you tend to do here are wrong. So remember the things you're supposed to do. You're supposed to make the positive direction for this the direction towards the center of the circle. If you didn't know that, you should write that down. So I'm going to make mg positive and the normal force negative, because mg is directed towards the center of the circle. I'm also going to replace centripetal acceleration with v squared over h, because h is the radius of curvature. And I'm going to list this as the max. This is as fast as I can go. We're looking for the max. Now, when I look at this relationship, the thing I'm supposed to point out to you is that the mass of the car is having something subtracted from it. If I want to go faster, I need to subtract less. You follow me? I mean, if the car wasn't moving, if this were zero, the normal force would just be mg, because the net force would be zero. But if I want to have any velocity, then part of the weight is helping me go over the top of the circle and stay in contact with the ground. The smallest the normal force can be is zero. It can't pull, it can only push. So as I make v bigger, n gets smaller. The smallest that can happen is when n is zero. So my maximum occurs when n is zero. So that's what Vmax will be. Mg equals m Vmax squared over h. And that tells me right away that Vmax is the square root of gh. Now, we now know how fast the cars can be traveling at the top of the hill. We want to know how much we have to pull the spring back to make this happen. This is question E. Right? We successfully answered question D. Now we're answering question E. At the top of the hill, the car is going to have kinetic energy. We just saw that it can have some kinetic energy. But it's still also going to have gravitational potential energy. It's above the reference level. So we want to find out how much can we pull the spring back and still safely make it over the hill. This is our threshold value. So let's put all those things together. I'll have mg times 3h plus 1/2 k x squared. That's from this. That has to equal 1/2 m Vmax squared plus mg times 4h. That's from this. Now, we have a substitution to make for v. All right, that's why we solved for Vmax a minute ago. So let's do that substitution. 1/2 times m times gh squared plus mg times 4h, all equals mg times 3h plus 1/2 k x squared. That's a whole lot of stuff. But a reminder, we're looking for x. How far can the spring be pulled back? So I was going to focus us on the algebra here. At this point, if you can get all this together, you're getting most of the points. This is a lot to bring together. You know, a point for subbing in the velocity correctly, a point for setting up the correct energy equation at the top of the hill, a point for setting up the correct energy equation when you're back up against the spring. Right, you see how the partial credit will probably be awarded? But now, a point for doing your algebra. If you wanted to get this last point, one of the things you have to do is be good at doing your algebra. I'm going to square the GH and get 1/2 mgh plus 4 mgh minus 3 mgh. Just going to bring that over to the other side. And that's going to be 1/2 k x squared. Looking for x. Those all have mgh in them, so I can just add them together. 4 minus 3 is 1. 1 plus 1/2 is 1 1/2. So this is 3 halves mgh. The right side is 1/2 kx squared. So I'm going to solve for x. X equals, cancel out the 2's and get the square root of 3mgh over k. It's a lot of algebra. This can be intimidating, but it is just algebra. Well, do you have to pull it more or less? Well, you're comparing this with this. Clearly, you have to pull it back more. Why? It needs more energy. At the top of the hill, it's going to have kinetic and potential this time, not just potential. And so this is where it gets its extra energy from.